Okay, I now want to introduce Tommy Thomas, who's the, I guess you're the CEO and CTO.
Oh, we don't really have a CEO.
Oh, okay.
Just the CTO.
It's the CTO of Third Dimension Technologies and also developing a number of very interesting light field display systems. So let me hand it over to you. Leslie.
Okay. It's a pleasure to be in front of so many very smart people. It's really quite a gathering. So we've developed what we call a holographic angular slice 3D display. We're Third Dimension Technologies. We're located in Knoxville, Tennessee. We have 3 different products. We acquired digital holograms. I won't talk about that, but we can do a nanometer scale measurement by acquiring a phase and amplitude. So if you've got phase, you can measure it to 1,000th of a wavelength or so and do extremely fine scale measurements. We have the holographic angular slice 3D display, which we're going to talk about, and we've used that, integrated that into a deployable flight training simulator for the Air Force, 5th generation simulator for the Air Force. I've got some of our principals here, myself, Paul Jones, Steve Kelly is in the back operating the video equipment, and we have a physics technical support, Andrew Smith. Here's a short outline, so we've split the presentation into 3 pieces, and I better talk fast. I'll probably run out of time. We're going to talk about the electronic holographic stereography, or the holographic angular slice 3D display. We're going to talk about rendering. If you take a program that takes 3D data and renders it for 2D scenes, and then you try to display that on a 3D display, it looks awful. So we'll talk about that for a little bit. And then some thoughts on a streaming media field of light display 3D standard, which is why we're holding the workshop. We're trying to learn as much as we can about sources and sinks and how to transmit that data. So if we talk about forms of holography, everybody first thinks about Princess Leia. Well, it's the first problem with, we seem to have skipped a couple here. First problem with that is it's not really a hologram, but that's another story. But you have to scatter light off of something. So if you're going to have it out in free space, then you need to ionize the air so that you can scatter light off of ionized air. Well, that takes a lot of energy. It's also dangerous. If you get close to it, you're going to get hurt. So when are we going to have Princess Leia type displays? Well, you could also do it with smoke and water. Those are kind of problematic also. It requires R2D2, and it's going to take a long time. We just heard a talk about diffractive holography. The problem there, as Lloyd very succinctly pointed out, is that you need effectively small pixels. I've written a very simplified form of the diffraction equation where lambda is a wavelength, d is your pixel size, and theta is your angular field of view. If you solve that for how much data, you need 10 to 500 terapixels. You need 500 nanometer pixels, and if you're going to fill a 30-inch display, you need around 7 to 10 terapixels. Well, and then you have to transmit it. So then you start getting up into those hundreds of terabytes. You have to analyze it, and you have to transmit it. You start getting up in that hundreds of terabytes range of computation and of transmission. So back in the 1970s, people developed something that's much simpler than a diffractive hologram. It's a holographic stereogram. The analog ones, you made about 100 pictures with a camera, analog camera, and then you used laser light to make vertical hologram strips on a photographic plate, and then you could replay that either in white light or laser light. If you've ever seen a white light hologram, it was a holographic stereogram. Most of you have probably seen that. That takes 20 to 100 megapixels, and we can do that today. I mean, that's a piece of cake, right? Anybody can figure out how to analyze that much data and transmit that much data. It's horizontal parallax only. Let me go back up here. I'm skipping slides here. This is an array of 23 projectors. It produces a 23-degree wide horizontal field of view by 90 degrees vertically, so a very wide field of view. You get 3 megapixels into each eye from any particular position, from any viewpoint. This is a schematic of how an electronic holographic stereogram works. So each projector produces a full 2D image. That 2D image fills the screen, and the light is pointed in the direction of the actual 3D point. So the projectors are spaced 1 degree apart, and the images are rendered to be 1 degree apart. And so the light from the projectors hits our holographic optical element screen, which diffuses the light 1 degree horizontally and 90 degrees vertically. And the 3 points we've illustrated here all point at the actual 3D point, and so the light from the 3 projectors, the light beams, the pixel representing that 3D point, they all converge together at the actual 3D point, and it forms a piecewise linear approximation of the real 3D wavefront. And so you get a different view into each eye. Different projectors will hit each eye. They're separated by 1 degree. The diffusion is Gaussian, so we calibrate, we overlap the projectors. The Gaussian, is very wide, so it's 1 degree full width at half max. And so you're actually seeing the light from 3 projectors at any single time into each eye. Actually 5 if you count 10% contributions. So that's basically how it works. It creates the best focus for your eye from those 3 projectors is at the actual 3D point, and your eyes point at the actual 3D point. So there's no vergence accommodation mismatch. So this has all human visual cues. It reproduces everything. It's like looking out a window. Now you do not have vertical parallax. Most people don't bounce up and down, don't use vertical parallax very much. Your eyes are separated horizontally, but your eyes point and focus at the actual 3D point. It does not make you sick. If you get sickness staring out a window, then you might get sickness staring at this display, but it's not going to give you display sickness like you get from stereo 3D. Most of you are probably familiar with being a little bit uncomfortable watching stereo 3D, or some people actually get physically ill and can't watch stereo 3D, glasses 3D, or lenticular 3D at all. Here's some pictures, actual images from one of our displays. We moved the camera to the left and moved it to the right, and you can see the parallax in the image. This was one of our smaller displays, older displays. But you can see that the colors are bright. If you were seeing it in person, you could move all the way through that range and the image would change continuously. So there's no dead zones, there's no pseudoscopic viewing, it's all correct. It does the right thing as you move left, it does the correct thing as you move left and right. This is another example. This is just the left view, full left view from one projector, and the full right view from the other projector, and you can see that you can look around the Coke can and see the tennis ball behind it. So comparing full parallax, we just heard Dr. Lacombe talking about full parallax, and he explained the problem very succinctly, which is the full parallax is an n-squared problem. If you've got a 12 projector or a 12 view array, then for full parallax you need 144 views. For horizontal parallax only, you only need 12 views. If you've got 12 degrees of look around and you need 1 projector per degree, then the cost is down by the square. It's a square root of what it costs for full parallax. Again, your eyes are separated horizontally. They're not separated vertically. So now we do see people bounce up and down in front of our display occasionally, and it does give you the view if you move your head up and down, the view follows you. It doesn't change vertically. Most people will do that once. If you really need the parallax in the other direction, you can always spin the object to get the parallax in the other direction. Here's a picture of our 12-channel display. It's made from 12 inexpensive Pico projectors. These particular projectors are a half megapixel each, 800 by 600. It's run by a single gaming computer with 3 graphics cards. It's got a 12-inch horizontal viewing box at 5 feet. You can move your head 12 inches left and right. At 5 feet, 1 degree is 1 inch, and that's where the 12 inches come from. The projectors are separated by 1 degree with respect to the screen, and the screen is reflecting them out in a 1 degree. The holographic optical element screen is reflecting them out at 1 degree diffusion. It's a full screen view within the viewing box, so you can see everything. You see the whole screen. You're not seeing just part of the screen. And you can have the viewing box, if you want it 30 inches wide, well, you just use 30 projectors. We're showing here a flight simulator program. This is, we'll talk a little bit more about it, prepared from Lockheed Martin. You can see a joystick on the desk there, and then the cockpit instrument panel, not in 3D on the left. The HAS 3D screen on the right is 30 inches by 24 inches. And then this particular display, you're getting 1.5 megapixels into each eye over the full 12-inch viewing range. This is a, I did it again. This is a drawing of our 3D flight simulator. I'm going to show you a picture of it later on. It has a 70-inch diagonal curved screen. It has a 22-inch wide viewing box for the cockpit. It degrades gracefully. If you move forward and backward, the view gets smaller as you move forward or smaller as you move backward, but you're still seeing 3D, and you're seeing 3D over the part of the screen that you see. So it has a sweet spot that's 22 inches wide and a couple of feet deep, but it degrades gracefully as you move around. This again has that 23 array Pico projector that you saw, high fidelity controls, and a panoramic cockpit display with the image generator under the Pico projectors. I'm going to try to run this flight sim video. So I can tell you that in person this is actually spectacular. It looks pretty good on the video, but in person you're getting 3 megapixels into each eye. You're getting full 3D. It's really, really a lot of people, it's not just us, a lot of people have told us that the display is spectacular. So I'm going to stop that there if I can find the mouse. So current projects, we've had a small project with the National Institutes of Health to produce a virtual anatomy table. We worked with Vanderbilt University on that, and we're going to propose a phase 2 project for that in April. We've been working with a major defense contractor on a very large interactive display where have a 13-foot wide interactive area where people could do training, interactive training, group training, and everybody would have a different view as they moved around that 13-foot area. The view would change continuously. On the right, you see a picture. This is literally a photograph of the flight simulator that we built for the Air Force, and you can see the cockpit with the panoramic cockpit display and controls and the 70-inch diagonal screen. This is the 30 by 24 inch. The cockpit simulator has a 70-inch diagonal. This one is more like a 40-inch diagonal. It's 30 by 24. We have run Biodigital Human. This is an anatomy program. No glasses or eye tracking required. You just move your head and look around things. It's got stereopsis and motion parallax, view changes continuously as you move your head, and you move your head to see a round object. The views are continuously blended, no dead zones, no image flipping. It's a computer blended, no vergence accommodation. This particular one is 1.5 megapixels per eye with we're using 25 lumen projectors, but because it only diffuses into 1 degree, it has an equivalent brightness of 5100 lumen. This is the slide I was talking about. I'm not going to go over it again since I already talked about it, but you can see it's got a beautiful view of the human body there. If you were in person, it would really be quite stunning. So now we're going to move on from talking about 3D displays to problems of 3D frames rendered for 2D. So most of the programs out there that produce 3D are actually rendering for 2D displays. We intercept one of the views and then re-render it 20 or 30 times for each of our projectors from a different viewpoint. When you do that just stupidly, if you just take a 2D rendered frame and try to display it on your 3D display, it looks awful. Here's an example of 3D rendered for 2D. This is Google Earth and a view of the Earth. And then after modifying it for view on the actual 3D display, that's what the photograph looks like. And here's another example. This is the London Eye. You can see it just looks awful. And then when you modify it to show on the 3D display, and you would be able to look around with the 22, 23 channel display, you'd have 22 degrees of look around. You could look around each side of the London Eye and look around the buildings, and very, very pretty, very nice display. This is an example of a control station that allows us to go from 2D rendered views to what we have to do to the data to make it look good in 3D. And I'm not going to go over all these things, but you can see that there's 8 or 10 different things that you can control. It also has an autofocus mode that works reasonably well. It could stand more development, but you can, in general, take data rendered for 2D and capture it, and then re-render it for 3D. Prepared, again, is like Lockheed Martin's flight simulator. They bought the rights to training and education from Microsoft. And on that flight simulator, we do also have to change the data position and how it's rendered so that it look good on the 3D display. And on that case, we use a camera control. We just control the position and angle of the cameras. And that essentially does the same thing as the previous control set that I was showing. And we can make the flight simulator look good. This is a photo of the flight simulator image. This is a refueling tanker. And you can see that it looks good. It's in focus over the whole range of the display. This was done from the, I forget whether it was 12 degree or 22 degree, but anyhow, very, very nice looking in person. All right, so we talked about problems. This is just in case you're making a 3D display and you're trying to put a shim in there and capture the data and then re-render it for 3D. Talk about the SMFoLD standard a little bit. So the HAS3D current data model, we need frame information is needed to create the view geometry. We need the relationship between the data, the focal plane, and the viewer to create a focus view with correct parallax and depth of field. We need that data, and we need to arrange it correctly. So we set the focal plane, depth of field, and parallax. The majority of data has to fall within the focal range of the display, and I won't go into a long discussion of that, but there is a depth of field of the display. If you get too close or too far, then you need to anti-alias the data or crop it out. It will start to go out of focus. Geometry is calculated from average depth and range. 3D source applications written for 2D don't provide adequate data. So titanium GL, which is what we call our insert, our slice, our interceptor that intercepts the 2D data and re-renders it for 3D, calculates the missing 3D metadata, but we really would like to see that metadata come in with the 3D frame rather than having to calculate it. So the metadata model for focus, this is just for focus now, there's lots of other metadata that you need. The average depth of data in the range of interest, the desired focal plane distance, and the data range, nearest and farthest point that you want to display. And then some of it may need to be clipped or anti-aliased or blurred if it's too far away or too close. Here's just some example use cases for different 3D programs. Google Earth, looking at the Grand Canyon, puts out about a half a megabyte frame size, and frames per second is not really You can move around Google Earth pretty fast on our display, but it's a static display, so you're not really talking frames per second there. New York City from about 490 meters. Again, a static view is 5 megapixels. So there's a lot more data there than there is representing the Grand Canyon. So a 3D frame size is 5 megapixels. A spinning globe from Google Earth is a couple of megapixels. And then down at the bottom, you can see the really high data rates. You get about 28 or 29 megapixels per frame from the flight simulator software. And we can run that at 28 to 22 frames per second, depending on how high the resolution is. We know how to speed that up even further. If you want to sign an NDA with us, I'll tell you how we can make that run at 50 or 100 frames per second. But we won't talk about that today. But anyhow, this is just some example frame sizes and frame rates for this. This is for the 22-channel display, and then the prepared data is for 12 channels of the 22-channel display. So it slows down enough if you try to run all 22 channels that we only run. And the cockpit view, 22 channels, 22 degrees, 22 inches is really too wide. The pilot can't move his head that much. So 12 degrees, 12 channels is more than enough for the cockpit. Source data challenge. There's many forms of source data. Again, talking about a streaming media standard. There's mesh data with textures, there's point clouds, there's light field of planoptic data, there's medical data. Depth is explicit or derived from the data. It's explicit with mesh. That makes it easy for HAZ3D for our display to display it. Calculated for planoptic. Now, I understand from John that maybe it's not so hard to calculate it. But at the time I wrote this, I thought that would be very difficult for TDT to handle. The planoptic data would be hard for us to create we need 22 2D views rendered from different angles. And of course, there's really not enough parallax in a single camera, although an array of cameras would do it. Our personal desired frame format, we'd like a stream of complete 3D data frames of graphics primitives. So everything you need to calculate a 3D view. We'd like to have API extensions for the metadata. For planoptic data type, we thought that an API might be needed to handle that and convert it to volumetric data for HAZ3D. Video data, we see 3 ways to handle that. That was talked about by the previous speaker, plus one. Convert it to RGB plus depth, so depth images. Convert it to object descriptions, more difficult. Or a sparse array of video streams that are just interpolated. So like the HEVC 3D encoding. Here's a possible data flow model. So we see at the far end there's some 3D source application or some source of 3D data. There's a streaming media standard, open standard source API, which creates a complete 3D frame of metadata plus data packets. There's some kind of source encoder, which is going to compress and potentially encrypt the data. It's transmitted through the cloud over to a display decoder, converted back to 3D frame metadata plus data packets, and then the SMFoLD display API interacts with the 3D display. Now, we show two-way communication. This raises a lot more questions than it answers. Source end questions. Should the source application be forced to create a common 3D frame format? Do we force a single 3D frame format? Can we do that? Or does the API provide converters to convert from separate frame formats to a single frame format? Or does the standard allow for different 3D frame types to be transmitted? Display end questions. If a common format is transmitted, do we force the display application to accept it? Do we say, display, you've got to take this data, it's your problem, it's not ours? Or do we provide converters to convert the data to a format that the display can easily handle? If multiple formats are transmitted, should we assume that the display can accept the transmitted format? You know, we assume that there's handshaking going on between the display and the source application, and presumably it could transmit a data type that the 3D display could handle. How about 3D frame types? If we allow different 3D frame types, and when I say a 3D frame, I'm talking about enough information to display a complete static scene. So that's what I mean when I say a 3D frame. There's enough information there to display a complete static 3D scene. What data types should be included? Planoptic light field, point cloud, clad, medical. What is the minimum number needed? Can we get down to one frame type? And that's really as far as we've gotten at this point. There's been a lot of work done in addition to what we've thought of here, and particularly the JPEG Plano group has put a lot of thought into this. So we've benefited from that.
Okay, thank you.
And just before I quit, let me invite any of you who would like to come to Knoxville, Tennessee. We have the beautiful 22 projector flight simulator 3D display until January 10th, when we have to deliver it to the Air Force. After that, we have we still have 2 other models, but they're not of the same quality as the one we're delivering to the Air Force.
Okay, if there's one question, maybe we'll, yeah, Howard.
I'll make it quick. It wasn't clear whether the observer would have to wear glasses. And,
No glasses.
Okay, so it's auto-stereoscopic.
It's
then.
the views continuously overlap one another. It's a Gaussian 1-degree diffuser, and the projectors are separated by 1 degree. They each project a full frame, a full 2D frame. And so you're seeing, it's a long story, but you're seeing 1 degree from each projector, essentially.
Gotcha. So you're using
And they're overlapped and computer blended so that it changes continuously. It looks just like the real thing.
right. You can use standard matte screens then, basically.
No, it's a holographic optical element that diffuses 1 degree horizontally and 90 degrees vertically.
Oh, it's a specialized screen. Okay.
That's right. That's right.
Okay, thank you very much.